Why is it when the one light in this circuit goes out, they all don't go out? Stay tuned and we'll find out why. Welcome back to the channel. If this is your first time here, I'm Robin DeMarco, the online physics teacher, and my passion is taking the mystery out of physics and helping to supercharge your science education. For the best information about physics tips and tricks, be sure to subscribe to my channel and hit that bell to be notified when I post a new video every Friday. In our series circuit video, which is linked in the description below and up here, we saw that there's only one path for the current to go through. And if there was the single break in that circuit, everything went out. But that's not always the case. Nowadays, many holiday light strings no longer go out if just one light does. Yes, you'll notice about a third of the lights go out at one time, but not all of them. So what's happening? What we have is called a parallel circuit. So let's head over to the whiteboard and the lab bench and see what's going on. I'm going to start with something most of us are familiar with: three parallel lines. Instead of just being lines, let's replace these with lights. And if we attach the power to both ends of the lights, what we then have is a parallel circuit. Now, if you remember from our series circuit lab, we were able to trace from one side of the battery all the way through, go through all three resistors, and come back to the other side of the battery. And we never lifted our finger. But let's try it here. What happens? We can't do it. We have multiple paths for the current to go through. So let's take a look at these paths individually. When we look at the voltage drop across each of these paths, what we see, since they're each tied directly to the power source, they have the same potential drop. So we notice that the total voltage is equal to V1, which is equal to V2 and V3. The current through each of these lines varies, however. Now, current is like most people. It wants to take the path of least resistance. So the path that has the greatest resistor, or the greatest resistance, is going to have the lowest current. And the path that has the smallest resistance is going to have the largest current. We know that going into the branch, or the branches, that it's all one current, and then it divides up into the three parts, and then it comes back into the final current at the end. So that tells us right away that the total current has to be the sum of the individual currents in the lines, I1 plus I2 plus I3. So for us to see how resistance in a parallel circuits work, let's take a look at Ohm's law. And we know that Ohm's law says the voltage is equal to the current times resistance. But I want to solve this now for the resistance. So R is going to be equal to V over I, voltage over the current. Now, to find the total resistance, I'm going to need to look at V1 over I1 plus V2 over I2 plus V3 over I3. The problem I have here is that I instantly see that I need to have a common denominator. And that's very hard to get with all these different resistances, especially when we work with real resistors. You'll find that in the lab, we like to use things that are nice and simple, 20 ohms, 30 ohms, whatever. But in reality, they might be 10,000 ohms, 612 ohms, and some other number. Very hard to always find the common denominator. So instead, what we do is we look at the fact that the voltage is the same all the way through the circuit. And so what we're going to do here is we're going to take and flip this around. So we're going to look at 1 over the total resistance, which is then going to be equal to I1 over V plus I2 over V plus I3 over V. It's going to give us 1 over R1 plus 1 over R2 plus 1 over R3 is equal to 1 over RT. Okay, so let's take a look at an example here. A circuit is powered by a 12-volt battery and has resistors of 20 ohms, 30 ohms, and 40 ohms, and are connected in parallel. Determine the potential drop and the current through each resistor, the total current, as well as the equivalent resistance for the circuit. So here's how we do it. We know that the total voltage is equal to V1, which is equal to V2, which is equal to V3, doesn't change. Therefore, it's going to be equal to 12 volts. The current in each of the legs is going to be equal to the voltage across the resistor divided by the resistance. So for example, I1 is going to be 12 volts divided by 20 ohms, or 0.60 amps. I2 is going to be 12 volts divided by 30 ohms, or 0.4 amps. And I3 is going to be 12 volts divided by 40 ohms, which is 0.3 amps. So our total current here, because they add up, remember, IT is equal to I1 plus I2 plus I3, is going to come out as 0.6 plus 0.4 plus 0.3, or 1.3 amps. Now, to figure out the actual resistance in the circuit, what we're going to look at is 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, or 1 over 20 ohms plus 1 over 30 ohms plus 1 over 40 ohms. And when we go through and do all the math on that, we find that this gives us a numerical value of 0.1083 per ohm. Now we have to take the reciprocal of that, obviously, and that gives us 9.2 ohms. Now here's a key factor. Notice what happened here. The total resistance in the circuit is smaller than the smallest resistor in the circuit. That's a key point. Now, some of you may say, well, wait a minute, couldn't we use a different method to find the total resistance? The answer is yes. You could have gone through and used Ohm's law again, since we do have the total voltage and we have the total current. So in that case, we just divide 12 volts by 1.3 amps, and we still get the same answer, 9.2 ohms. Okay, so there's the basics on parallel circuits. I'd like to find out, where else have you seen a parallel circuit? Drop your answers in the comment below. And if you missed my videos on series circuits, this would be a great time to go back and check it out. It's linked in the description as well. Now that you know how to identify and solve basic parallel circuits, and we've seen the relationship of voltage, current, and resistance, it's time to go out and practice a few and see how you do. If you haven't already grabbed your copy of my free PDF, 15 Tips to Improve Your Science Grade, the link for that is in the description below as well. If you found this video helpful, please let me know by liking it, subscribing to the channel, and do me a favor and share the link with someone else who could benefit from it. Thanks for watching. I'm Robin DeMarco, the online physics teacher, and I'll see you next time.